So let's jump in and try to do this integration question here. So we're going to use a substitution for x. So here's something I used to do when it came to integration and substitution. I thought that was x, so I was caught in the reality where I had to calculate this as a function of x, right? And that was a sec squared theta. And then I was always like, okay, so dx will change to, is it dx by d theta, and then yeah, so I did indeed substitute this in. But a lot of you may use another way, which is much faster, and it's just that trick of you have x is a tan theta, and we just sort of differentiate both sides implicitly. So we get the dx is a sec squared theta d theta. Okay, so what are we even differentiating with respect to? I don't know. I guess we're just differentiating, or like incrementing both sides, you could say. But that's saves us a lot of, confusion, because dx, we just substitute that right in there. Okay, so that's something to note. Now, continuing on in the actual question, what I'm going to do is, well, what will the bottom line become? That's a squared. Now, because x is a tan theta, that's going to be plus a squared tan squared theta. We append this on, so we get a sec squared theta, and we have a d theta. Now, if you notice here, the bottom line, let me change my color of pen just here. The bottom line is actually, the a will cancel, right? The bottom line will just be a up upon 1 plus tan squared theta. Top line is sec squared theta. And you'll notice that 1 plus tan squared theta is actually sec squared theta. Okay, so it's okay to cancel that and that. They're the same thing, because theta is non-zero. Yeah, we'll show for a not zero as well. Yeah, we haven't really defined the range, but as long as you write somewhere theta is not equal to 0, in other words, x is not equal to 0, then it's perfectly fine to cancel, and we're left with integrating simply 1 over a d theta, which gets you, well, theta over a plus c. But we want this back in terms of x again, because we don't really care about theta. So remembering that x is a tan theta, just take that and rearrange for theta. So divide both sides by a, and then take arctan. Okay, so we have x over a, just like that. And that is basically the answer there. So that's 1 over a arctan x over a plus some constant. Now, in order to do the next bit, which is, somewhat trickier, we have to think about what we're going to do here. Like, how does the first bit apply? So, if you'll notice, we have our x here, and it is squared as well, right? So what I'm going to do is try and apply this, right? So here we wrote x is a tan theta. So my first guess would be, well, could we write sine of x as a tan theta? Like, would that work? Well, if that's the case, then I guess it would, because the bottom line, again, would be 1 plus tan squared, and that would give us sec squared and stuff. What we do need to check is the differential of both sides. D theta. Okay. And that's quite interesting, because we see that dx cos x is actually directly that, and what's a wonderful piece of news is cos x is actually right on our top line here. So cos x dx we can just directly change into this, and again the bottom line is going to be 1 plus tan squared. Okay, so in other words, that literally just becomes, again, although we need to be careful about the limits here, So I'm going to change them in a minute. But that'll just become, again, 1 over a. Wouldn't it? Actually, I don't even need to have an a there. I could just say straight away sine x is tan theta. You know, because we arbitrarily chose a last time. By choosing a to be 1, everything will work out fine, and I'm actually left with the integral of nothing. Or in other words, just d theta. Okay, so what are our limits changed to? Well, you notice our limits for x were pi over 2 and 0. So sine of both of those gives me 1 and 0. So tan of what will give me 1? Well, tan theta has to be 1. So theta here will be pi over 4. And this will be 0. So you're integrating, you know, between the limits of pi over 0 and 4 of nothing. Will just give you, let me scroll over a bit here. That'll just give you theta bounded between pi over 4 and 0. In other words, the answer is pi over 4. Okay, I hope that was clear. You can work through it yourself and discover that, well, simply by substituting sine x for tan theta, which is fine to do, we're just literally applying what we did for the first part. And this is like the common way to do step. You look at the question and you're like, okay, well, you know, the first bit they give me there, obviously that must apply in some way to this question, so let me try and apply it. And in this case, it was, well, it worked out fine. Sine x is tan theta. Well, that's my way of doing it anyway. There's probably many ways to do this question, but that was a good spot. Now, we want to use the substitution t equals tan a half x. Now, this is very, very common. Okay, so if you're familiar with your tan substitutions, and if not, I'll write these down here, but this is something you should get very familiar with, right? T is tan a half x. This is used all the time in STEP. Okay. And the reason for that is I can have very nice expressions for sine of x and cos of x in terms of t. Okay, so basically if we have tan a half x here, you can use the half angle formula to write sine is 2 sine x over 2 cos of x over 2. Okay, now the neat trick here is to then have like divide and multiply by cos. In other words, we're not changing this expression. And you'll notice that this is 2 tan x over 2 multiplied by cos squared, or I'm going to write that as 1 over sec squared x over 2. Okay. At which point this becomes 2t multiplied by 1 over 1 plus t squared. Okay, so that's our expression for sine x in terms of t. Cos x, you're going to do something similar. Remember, there's a number of ways to write the cos double angle formula. But the one I'm going to use is 2 cos squared minus 1, which can be written as 2 over sec squared. Now sec squared, again, we said was tan squared plus 1. And that's just minus 1. So let's write 1 as a fraction with the same denominator. And we end up getting 1 minus t squared over 1 plus t squared. I would recommend deriving those yourselves and trying to memorize also those identities. So we have sine x being 2t over 1 plus t squared and cos being this. All right? And that comes in very useful. The last one we also want to have is dt is, well, what's it going to be? That's going to be a half sec squared. And again, sec squared is tan squared plus 1. So that's useful as well. Okay. Or in other words, the most common one is dx is 2 over t squared plus 1 dt. Okay. So you may or may not be familiar with all of these identities, but they you know, back in the day when A levels for maths were actually difficult, this was commonplace in most exams. So it's nice when you see this in your STEP paper when you sit it you should look for a question like this because, heavy reliance on this can be a good thing because the questions tend to get really easy once you understand the ideas behind this. Okay, so basically we want to show that this integral under the tan substitution is going to be half of, I there, right? So we want a cos x and we want a 1 plus sine squared x, all right? Well, to make things neater, I'm just going to move this over here, and we're gonna have a bit more room for us to write things with. Okay. Go away over now. Right. Okay. So I said that cos x was 1 minus t squared over 1 plus t squared. And we said that sine x was 2t over 1 plus t squared. So sine squared is going to be 2t squared over 1 plus t squared all squared. All right. Suppose we add 1 to that. Right, so sine squared plus 1 will be, well, if I add 1, it's the same as adding 1 plus t squared plus, 1 plus t squared squared. So I end up getting, if I expand this out, what happens is I end up getting 1. I'm going to have the 2t squared and then another 4t squared, so that's 6t squared. And over here I'm going to have t to the 4. And the bottom line will look like 1 plus 2t squared plus t to the 4. So that is sine squared plus 1. Sine squared x plus 1 under the substitution. That would be cos over here. All right. So what is cos divided by sine squared plus 1? Well, if we look at that, cos of x over sine squared plus 1. I'm just going to flip this fraction, and I'm going to get 1 minus t squared over 1 plus t squared multiplied by, well, I suppose it'd be easy to write that as 1 plus t squared all squared over this 1 plus 6t squared plus t to the 4. Now, the other thing I said was when we're changing our dx, dx was equal to 2 over 1 plus t squared. So we want that in there. Sorry, it's 2 over 1 plus t squared dt. So we want that in there as well. So we're going to get another 2 over 1 plus t squared dt. Okay? So effectively, that's what our integral there becomes. So if we give that a name, if we give that integral star, if we go star, if you neatly write that out, then star becomes that. Okay, where cancels, and we see that star is going to be, I think I've got twice of I there. Oh no, sorry, I'm working with I first, and I'm working with I. Yeah, I'm showing I is equivalent to star, so that's our I. But yeah, I mean, you can do the heuristics yourself. Basically, that is exactly equivalent to what we want. The 2 is a factor, so we have that twice of I is actually equivalent to this thing, which is the integral there, and you'll see the limits will match up perfectly well as well. The pi over 2 will change into the 1, and the 0 changes into the 0. Okay, so that bit, once you know your tan substitution, that bit's pretty easy to do. Okay, well, I'm not going to say it's easy, but it's doable, definitely doable. Okay, the next bit is somewhat more difficult because we have to take the ideas that we have just used and apply it to this. So so you see there's 14 there, that's different. So draw your attention to why is it different. Well, there's a 6 here. So how did the 6 get there? You know, what made the 6 so special? Well, the 6 came from the fact that we had our 2 there, and we were squaring that, and then we were adding 1. So this was just sine squared plus 1, and that's why there's a 6, because when you square that's how, it's a 4 plus the 2. So could we make that a 14 easily? Like, is there something we could do to turn that into 14? Well, I can't really change the 2, right? If I'm adding 1, if I'm doing the expression in a similar way, the 2 is kind of fixed, right? And this 2t squared, it kind of, unless I had a constant in front of this, I'm going to keep that 2t squared where it is. But what I could do is I could add some multiple of sine squared, right? And in fact, that's the key to doing the question. If I add 3 sine squared, what will happen now is I'll have 3 times the 2 squared. And that'll just give me 12, right? That's 12t squared. And then, of course, when you add 2t squared, that'll just change to a 14. So in other words, you end up showing the expression here is equivalent to something along the lines of cos x over 1 plus 3 sine squared x. And that's most of the hard stuff out of the way. Now, just like the start, we now have to evaluate that, right? I'm pretty sure it's going to look something similar to this. You can try to do it yourself and figure out. But then, what's going to happen here? Well, how do I evaluate that? Well, again, I'm going to use the substitution. I probably bring the 3 in this time. And that's tan squared. I know the one we did at the start. I'm missing that here. Hang on. Yeah, that's just going to be tan a tan theta, I guess. Or maybe even 3 tan squared, just going to tan theta and then seeing what happens there. But yeah, because that'll just be a constant. If you differentiate that, it's pretty much similar to part 1. So that's the main ideas behind this question. There's nothing too difficult behind it, really, once you start thinking about them in the right mindset. Integration was one of my favorite topics when I did this, because it was something I actually saw myself improving at the more I did. You just picked up little things like this. So that's today's video. I hope you guys found that helpful. I'd be interested to know if any of you did it in a different way, or if there's any problems with my methods, just point it out and I will correct it or whatever. So cheers for watching.